Okay, hi everybody. So in this video, I want to prove the following theorem, which is that if I have an m by n matrix A, then the column space of matrix A is a subspace of Rm, okay, where Rm is now the codomain of this matrix. Okay, so it's not surprising that we tack on this word space to column space and null space. It's because they happen to be subspaces of either the domain or the codomain. So in the case of the column space, what we're claiming here is the column space of the matrix A is a subspace of the codomain, which is Rm. And so one really quick proof of this would be to use the results that we've already proven, namely this column space of matrix A, we can write as the span of the column vectors of matrix A, and we've proven that the set spanned by a set of vectors is by definition going to be a subspace of the larger space where those vectors live. But let's prove this using the definition of subspace so that we can get some practice with those properties. So in other words, let's show that first of all, the zero vector is in the column space, that the column space is closed under our usual vector addition operation, and that the column space is closed under scalar multiplication. So for the zero vector, we can just pick weights of 0 for all of the column vectors. So I can take 0 times a1 plus 0 times a2 all the way up to 0 times an. And when I take that linear combination, we get the zero vector. So therefore, the zero vector is in the span of the column vectors of A. So it is in the column space of matrix A. Let's check the vector addition operation to make sure that it is closed. So if I have two vectors u and v in the column space of A, that means vector u I can write as some linear combination of columns of matrix A. Vector v I can write as some other linear combination of these column vectors. And now when I add these two vectors in the typical way, we could group our terms. So this would simplify to x1 plus y1 times a1. So this is now the weight for column vector a1. And then I have x2, y2, a2, and so on, all the way up to xn plus yn times column vector an. So I've just written this sum u plus v as a linear combination of the column vectors of matrix A. So this sum u plus v is in the column space of matrix A. So it is closed under addition, vector addition. For scalar multiplication, if I take some vector u in the column space of A, and let C denote any arbitrary scalar, then let's consider the scalar multiple of C times u. So that would look like, since u is in the column space of A, right, it is a linear combination of column vectors of A. And now when I multiply this scalar, we just distribute it through every single term. And now I can see that C times u can also be written as a linear combination of column vectors of matrix A. So C times u, therefore, is also in the column space of A. So the column space of A is closed under scalar multiplication. So this verifies that the column space is indeed a subspace of the codomain, which is Rm. All right, hi, welcome everybody. So let's continue our exploration of matrices, m by n matrices A, and the various subspaces that we can define from these matrices. So we've talked about the null space of a matrix A, we've talked about what the column space of a matrix is, and similar to a column space, we can define what's called the row space of an m by n matrix A by, so we would denote this row A, and this would just be the set of all linear combinations of the rows of matrix A. So matrix A is m by n, so it has m different row vectors, and each of those row vectors would be a vector inside of Rn, which is the number of columns in this matrix. So the row space we could just write as the span of all of the different rows. And as with the column space, we might want to keep in mind that we might want to think about what is the minimum number of vectors that we would need in this list to generate the full span. But that's a topic for the next section that we'll get into. So for now, for example, if I have this same matrix A that we've been working with, this 2x5 matrix, then the row space of matrix A would be the span of the column vector, or excuse me, of the row vectors of this matrix. So that would be 3, 6, 6, 3, 9 as one vector, and then we have a second one as 6, 12, 13, 0, 3. And another way that we could have found this row space would be to take this matrix A and write its transpose. So this would now result in the first column would be 3, 6, 6, 3, 9, and the second column would be 6, 12, 13, 0, 3. So the transpose would be a 5x2 matrix, and then we can go ahead and pull off the column space of this transposed matrix, which would give us exactly the same vectors that we have down below.